An infinite sequence is a list of numbers that go on forever and follow a specific rule or pattern. So here are some ways we can represent infinite sequences where the subscript n goes from 1 to infinity. And in this example of an infinite sequence, which follows this rule, the numbers in the sequence can be represented on a real line or graphically. So what we have is 1, 1/2, 1/3, 1/4, 1/5, and so on. So you can see that for a large n, the numbers in the sequence get closer and closer to 0. And here is an example of a sequence that oscillates according to the powers of -1. So it looks something like this. To prove the limit of a sequence, the epsilon-delta definition is used. So this states that the absolute value of a term in the sequence minus the limit is less than some small number epsilon for all n greater than some integer n. So for example, we can see that when n equals n, all the terms an beyond this number fall between the limit plus epsilon and the limit minus epsilon. So you can see this by rewriting this inequality as follows. And then adding L for all these terms, we obtain the following inequality. And you can see that graphically over here, where all the terms beyond n fall in this range. But typically we don't apply the epsilon-delta rule, because we typically just want to find the limit of a sequence. And we thereby apply the rules for limits that we learned earlier for functions. Let's prove the limit of this sequence. So the formal definition is that for every number greater than 0, then there exists an integer n such that for all n greater than n, the difference between every number in that sequence minus the limit is less than epsilon. So for example, if n equals 2, then every number in that sequence beyond 2 must fall within this region for the sequence to converge. So using the rule for our sequence, which is 1 on n, minus the limit we're trying to prove, and taking the absolute value, and this must be less than epsilon. So therefore, we obtain 1 on n is less than epsilon, because n's are all positive. And flipping this equation around, we get the following inequality. So therefore, if we choose epsilon is equal to 1/2, which is a good value to choose based on the behavior of this sequence, then basically n must be greater than 1 1/2, which is 2. So therefore, for this value of n equals 2, every number in the sequence beyond 2 must be less than epsilon, which is 1/2. And you can see that 1/3, 1/4, and so on are all less than 1/2, and the sequence converges. Let's determine if the following sequence converges. And this is done in much the same way as when we evaluate the limits of functions. Because this sequence behaves like a function, except these numbers are discrete integers. So what we do is multiply by the reciprocal of the fastest growing term in the numerator and denominator. So we end up with the following limit. And therefore, taking the limit of each term individually as n goes to infinity, the following terms go to 0. And therefore, our limit is 4/3. Let's determine if the following sequence converges. So again, we multiply by the reciprocal of the fastest growing term. And you can probably see, because the fastest growing term is in a numerator, the sequence is going to diverge. But let's continue to evaluate the limit, which we can now write in this form. And now we can take the limit of each of those terms as n goes to infinity. So these ones are going to basically drop out. And we end up with the result of 1 on 0. So therefore, the sequence diverges. Let's determine if the following sequence converges. Well, these numbers are discrete integers, as we can see. And the equivalent continuous function that passes through all these numbers in the sequence is x to the 1 on x. So these are real numbers as opposed to those integers. And now we can apply logarithms and exponential functions to evaluate the limit. So if we take e to the power of the natural log of the function, we obtain the following result. And we didn't alter the function. And due to the continuity of the exponential function, we can take the limit inside that exponential function. And applying rules for logarithms, we can write the natural log of x on x. And now we can recognize that as x approaches infinity, the term in the denominator grows faster than the term in the numerator, which you can verify using L'Hopital's rule. So we obtain e to the 0, which is equal to 1. And you can verify that this sequence converges to 1 by putting in large integers in your calculator. So for example, 1 million to the power of 1 over a million.